Okay, hello everyone. In the beginning of today's class, let us see new announcements. Okay, the first new announcement is May 23rd, 2022. Class videos uploaded. Hello everyone. I have uploaded the class videos on May 23rd, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. The second new announcement is the slides of Chapter 4 has been updated. Oh, sorry, this should be half. Okay, let me edit it. Okay, half. Okay, have been updated version 2022-0525. Hello everyone, I have uploaded the latest version of the slides of Chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website. Multiple input, multiple output techniques for wireless communications. Course content, slides, Chapter 4, slides 2022-0525.pptx. Best regards, Wei Zhen. Okay, the third new announcement is the handout of Chapter 4 has been updated, version 2022-0525. Hello everyone, I have uploaded the latest version of the handout of Chapter 4 to the eCourse 2 website. The location and the file name are eCourse 2 website. Multiple input, multiple output techniques for wireless communications. Course content, handouts, Chapter 4, handout 2022-0525.pdf. Best regards, Wei Zhen. Okay, next let us see the progress of the last class. In the last class, we have taught to Chapter 4 slides, page 93, figures 4.9, caption unfinished. Okay, please open the slides of Chapter 4. Okay, and please turn to page 93. Okay, excuse me. So figure 4.9 shows an example of a measured multi-pass delay profile in a residential environment when there is a direct pass component combined with scattering. Frequency is 850 MHz. Okay, it is from reference 19. Okay, let us see reference 19. Okay, this is reference 19. Okay, this is a journal paper. The author is Devasarvathan. Okay, and the title of the paper is Time Delay Spread and Signal Level Measurements of 850 MHz radio waves in building environments, which was published in IEEE Transactions on Antennas and Propagation in 1986. Okay, so the x-axis is time in microseconds from 0 to 1.8 microseconds, and the y-axis is the relative power from negative 80 to negative 30 dB. Okay, so we can see that as time increases, the relative power will decrease. Okay, also not in a monotonic way. Okay, next let us see figure 4.10, example of a measured multi-pass delay profile in a residential environment in the absence of a direct pass component. Frequency is 850 MHz. Okay, this figure is also from reference 19. Okay, from this reference. Okay, so the x-axis is also time in microseconds from 0 to 1.8 microseconds, and the y-axis is the relative power in dB from negative 110 to negative 60 dB. Okay, and the environment is residence number 1. Okay, we can see that as time increases, the relative power decreases, also not in a monotonic way. Okay, so figures 4.9 and 4.10 show examples of measured delay profiles in residential outdoor environments with and without a direct pass component. These examples show two typical characteristics of delay profiles. First, they show that there is a general, though non-monotonic, trend towards weaker power as the delay increases. Okay, so we can see that the delay, which is the time, increases, the relative power is weaker. Okay, so in the figure 4.10 we can observe the same phenomenon. This fall off in power is due to the fact that larger delay values are associated with energy that has propagated over a longer distance, resulting in greater propagation loss. Okay, because when the delay is larger, that means the path is longer. Okay, the distance is longer. When distance is longer, the path loss is larger. Okay, so the received energy or the received power is smaller. The second feature we see is that there are bumps. Okay, what is a bump? Let us see the handout. B-U-M-P. Okay, bump. Okay, so this is page 96, problem 1. What are bumps? Solution: to travel, usually in a vehicle, in an uncomfortable way, because the surface you are moving over is rough. Okay, bumps in the delay profile. Okay, let us go to the figure 4.9. Okay, so you can see that there are bumps, here. Okay, and in figure 4.10 there are also bumps, here. Okay, in the delay profile, indicating that there is more energy associated with some delays than others. Okay, for example, in figure 4.10, when the time or delay is 1.1 microsecond, this point, we can see that it has the largest relative power. Okay, so it means that it has larger energy here. Okay, this is caused by the scatters not being uniformly distributed in space. If, for example, there were only a small number of discrete scatters, then the delay profile would consist of discrete spikes. Okay, what are spikes? Let us see the handout. Okay, page 97, problem 1. What is a spike? Solution: a narrow, thin shape with a sharp point at one end, or something, especially a piece of metal, with this shape. Okay, so spikes. Okay, what are spikes? Okay, for example, like this. Okay, it is a spike. This is a spike, and this is a spike, and this is also a spike, like this. Okay, spikes corresponding to the propagation delays of the paths between the transmitter and each of the scattering objects. In most realistic environments, there are a very large number of scatters distributed throughout space. Okay, for example, in my room, there are many scatters. For example, my computer, my monitor, and keyboard, and the mouse, speaker, and the mainframe of my computer, and the desk light, okay, and my chair, my table, my microphone, okay, etc. Okay, there are so many scatters in my room. Okay, so the delay profile is not discrete. However, because the scatters are not uniformly distributed, some delays have more energy associated with them than others. Okay, we will see later, see what does the scatters are uniformly distributed mean. Okay, it is called the Clark's model. We will see later in the slides. Okay, let us see next. Let us see definitions of Tm. Okay, the delay spread. There are two commonly used definitions for the delay spread of channel. First, it is important to emphasize that normally when defining Tm, okay, the delay spread, all delays are specified relative to the delay associated with the direct component of the transmitted signal, which is the first component of the signal to arrive at the receiver. When specifying the delay relative to the direct component, the delay is referred to as the excess delay. The delay spread is normally specified either by A, the mean excess delay, tau bar. Okay, when you see a bar above a symbol, okay, it usually means the mean or the average of this symbol. Okay, B, the RMS. Okay, RMS means root mean square, excess delay, sigma tau, which are formally defined as follows. Okay, oops, the equation number is in the wrong location. Okay, let me correct it. Okay, should be this, and 4.22. Okay, should be this. Okay, and 4.23. Okay, should be here. Okay, good. Okay, first, tau bar is equal to summation k phi c of tau k times tau k divided by summation k phi c of tau k. Okay, do you remember what is the function phi c? Okay, let us go back to the earlier slides to see the definition of phi c. Okay, let us see. Okay, phi c of tau is called the multipath intensity profile, the delay power spectrum, or the power delay profile of the channel. Okay, this is the function phi c. Okay, let us go back to the slide. Okay, this one. Okay, so you can see that it is and the tau k is the delay of the case path. Okay, so it is the discrete case. Okay, so you can see tau bar is a kind of weighting average of tau k. Okay, and the weightings are phi c of tau k. Okay, and sigma tau is equal to the square root of tau square bar minus tau bar square, where tau square bar is equal to summation k phi c of tau k times tau k square divided by summation k phi c of tau k. Okay, compare equation 4.21 and 4.23. You can see that the only difference between them is that here is the tau k and here is tau k square. Okay, this is the only difference. Okay, so so this is also a kind of weighting average of tau k square, and the weightings are phi c of tau k. So from the viewpoint of probability, if we treat c tau as a random variable, then tau bar is the mean of the random variable, and the tau square bar is the second moment of the random variable tau, and sigma tau, which is equal to the square root of the second moment minus the square of the mean of tau. Okay, so you can see that it is the standard deviation of tau. Okay, so we use sigma tau here. Okay, where sigma, we usually use the symbol sigma to denote the standard deviation of a random variable in probability theory. Okay, let us see example 4.1. What are the mean and root mean square excess delay spread values for the power delay profile in figure 4.11? Okay, let us see figure 4.11. Okay, figure 4.11 is an example power delay profile. The x-axis is tau, which is the delay. Okay, and the y-axis is the power. Okay, we can see that when tau is equal to 0 nanosecond, there is an impulse, and the amplitude of the impulse is equal to negative 100 dBm. When tau is equal to 100 nanosecond, there is the second impulse, and the amplitude of this impulse is negative 103 dBm. When tau is equal to 200 nanosecond, there is the third impulse, and the amplitude of the third impulse is also negative 103 dBm. Okay. Answer: start by computing tau bar. For convenience, denote negative 100 dBm by P. Okay, it follows from equation 4.21. Okay, let us see equation 4.21. Okay, in equation 4.21, okay, tau bar is equal to this equation. Okay. Okay, so tau bar is equal to summation phi c of tau k. Okay, so first tau is this, and the power is equal to negative 100 dBm, which is equal to P, and the tau k is equal to 0. Okay, so the first term is P times 0, and plus the second term. Okay, for the second tau k, the power is negative 103 dBm. Okay, compare with negative 100 dBm. It is negative 3 dB smaller than 3 dB smaller than this value. So as we know, 3 dB is approximately 2 times. Okay, so the power of this impulse is equal to 0, is approximately 0.5 P, and the tau k is equal to 100 nanosecond. Okay, so we write 100 here. Okay, similarly, for the third impulse, the power is also 0.5 P, and the tau k is equal to 200 nanosecond, and the denominator is summation k phi c of tau k. Okay, so which is equal to P plus 0.5 P plus 0.5 P. Okay, so after some simple calculation, we can know that the denominator is equal to 2P. Okay, and the numerator, the first term is equal to 0. The second term is equal to 50P, and the third term excuse me. And the third term is equal to 100P. Okay, so 50P plus 100P is equal to 150P, and we can cancel the P in the numerator and the denominator, so it is equal to 150 divided by 2, which is equal to 75 nanosecond. Okay, next, compute tau square bar. It follows from equation 4.23. Okay, let us see equation 4.23. Okay, we can see that tau square bar is equal to summation k phi c of tau k times tau k square divided by summation k phi c of tau k. Okay, compare with equation 4.21. We only need to add a square to the term tau k. Okay, so it is easily to write down the equation for tau square bar. Okay, we only need to add a square, and a square here. Okay, and we have this equation. Okay, and the denominator is equal to 2p again. Okay, it is 25 minutes. Let us take a break.